you hear me? Yeah. I have to change that fact with my face. It was from the COVID period. Okay. So, I will try to speak a little bit about games optimization and how theory can drive a little bit the thought of nowadays development, both in industry and theoretical multi-agent optimization. So, okay, let's see a little bit what is the background that we have. Like if we have been 20 years ago in that place, I don't know if Simons exist, but we will have a discussion about a single agent that is trying to optimize a function. It could be an LP, I don't know what it would be. But currently, the whole idea that we are trying to tame is that we are multiple people, that we're trying to solve different problems, that we have our own incentives. And I think that, I should not convince you that this is what is happening nowadays, because in the majority of the cases, the problems that we're trying to optimize, either they are separated in different servers, or there are sometimes that, we have multiple agents that they are trying to collaborate just to solve a task. And I mean, I strongly believe that I should not convince you that we are speaking about the rise of AI-driven multi-agent learning. Like, there are multiple examples, but given the fact that the half of you use your GPS in order to find out the Maxwell parking, so you solve the congestion problem in order to find your parking today at morning. I think I can convince you that there are multiple cases where either explicitly there are games that you are playing using AI as an advice tool, and sometimes the problem is implicit, like where in machine learning many times we're trying to develop like an architecture that would be like a game against the uncertainty, against the privacy that we want to not to leak, and so the question is like, okay, my claim is the following: even if we are 30 years ago, multi-agent games were here, okay? What is the difference? The difference is that now is the period that we started using AI architecture for our policy making. And now, if we're going back to theory, you will listen stuff about NP hardness or PPAD completeness, which means more or less that there is a complexity class that says that this problem is difficult. But in practice, you park at Maxwell parking. So let's find out what are the hidden structures that we are not discussing in that worst case theoretical examples. So all these problems are not just general sum problems. Typically, there are problems that they have some hidden structure. My claim is that in the majority of the cases, we have a convex penalty function like hinge loss, like a squared loss. And the only idea is that we will compose the loss of our problem with the neural net, that it is the advice machinery in order to take our decisions. And that will destroy all the convexity of our problem. And the main issue is that we have indirect competition. Like, we do not optimize over our strategies. The only thing that we can do is like optimize our parameters in our neural net and find out what would be the result that the neural net will have. So to formalize it even better, like a good fellow in a tutorial that gave, he said, I loved all these results about equilibrium and difficulty, but all of them in the main discussion, they are updated directly in the functional space. In practice, the players are represented with deep neural nets, so we have to understand what is happening in the parameter space. So what I want to speak about is the idea of hidden game. More or less, it is what I express in that image, that typically we're playing games. Most of them, they're monotone convex games. So if we were able to choose over the action space, it would be an easy game. The issue is that the action space is huge. So what we are doing a function approximation using a neural net. This is what we call hidden game. This is the formal definition of what exactly I say. I have a parameter space. I have like a map. This map is typically my neural net that chooses from the, this is the weight of my neural net, and I will take my action. This is what is happening in practice. This is all these amazing examples that we see from Go or any AI-driven game. The first result that we had was that yes, just gradient descent ascent cannot solve this problem. Actually, we can prove that we have such kind of recurrences. I say we can prove that we have such kind of recurrences, not experimentally. Very recently, we achieved to develop an algorithm that can solve such kind of non-convex games. But there are multiple interesting questions in order to make it applicable in practice, like how you can make it independent and not a centralized algorithm, how you can parallelize it, how you can make it private for every player, and what are the theoretical guarantees that we can give. That's all. Thank you very much.
We have time for one question, maybe as the next speaker steps up.